Now we're going to look at graphing these rational equations or functions as well as reciprocal functions. So to start with, we're going to talk about what it means to be undefined. So if you think back to Math 1, where we talked about graphing our lines and the slopes of those lines, and whenever we had a vertical line, our slope was undefined. And that's because whenever we did rise over run, we ended up with a number over 0. So anytime you divide by 0, that's what makes it undefined. So if I'm looking at a rational function and I want to know where it's undefined, I'm going to set my denominator equal to 0. So I would say x squared minus 3x minus 28 equals 0, and I want to know what values of x make this equal 0. Well, this is a quadratic that I can now solve. One way of solving quadratics is a factor, so this is a plain Jane, so I want to multiply to negative 28, add to negative 3, so that's going to be 7 and 4. And I need one positive, one negative. Because I want to add to a negative, the bigger one has to be negative. So then I can go from here to solve, set them equal to 0. So x minus 7 equals 0. X plus 4 equals 0. Add the 7 over, so x equals 7. Subtract the 4, x equals negative 4. So when x equals 7 and when x equals negative 4, if I plug those x values in, I get a 0 for my denominator, so it makes it undefined. So then if I look at my answer choices, that one's going to be C. Okay, so undefined means you're trying to divide by 0, which we don't want to do. Alright, so a reciprocal function is it's like the opposite of a linear. So it's what we say 1 over x. And so the shape of it is what we call a hyperbola. Okay, so we've got two almost exponential graphs going on. One on the top right, one on the bottom left. Alright, your domain and range is all real numbers, and it says all non-zero real numbers because we have two asymptotes on our reciprocal hyperbola. One of them is at the y-axis, and the other one is at the x-axis. So for our parent function, 1 over x, both of those are 0. So at y equals 0 and x equals 0, we have asymptotes. Alright, it's important to remember that your parent function is top right, bottom left. So it's in quadrants 1 and 3. Alright, when we look at our parent function, just like all of our other parent functions, we have those letters A, H, and K. Right, so for this one, the A is on top instead of out front. Okay, so you have A up top, and then with the X is always your H, opposite sign, and then the K is on the outside by itself. Alright, one thing to keep in mind, if you want to find those asymptotes very easily, you look at that HK point. So if you find that HK point, that's where your asymptotes intersect. And that's going to make it easy for us to graph. You just find that HK point, and that's where they intersect. Alright, that A value is going to tell us two things. It's going to tell us, one, if it's in quadrants 1 and 3, so if it's a positive A value, or if we reflect it and it's a negative A, it becomes quadrants 2 and 4. Okay, so 1 and 3 normally, 2 and 4 if it's reflected. And then that A also tells us if it's stretched or compressed, so if it's pulled away or if it's getting closer to that intersection. Alright, so for our example, I want to graph negative 1 over x plus 1 plus 3. Alright, so this negative 1, that's my A value, so that's going to tell me the 1 doesn't change anything, and then the negative is going to reflect it. So instead of being in 1 and 3, it's going to be in 2 and 4. Okay, my H value is going to be a negative 1, and then my K value is positive 3, so that's where my graph intersects, my asymptotes intersect. So if I go to graph, I'll sketch my x and y axis here. I'm going to go to negative 1, 3, and put a point. Just remember that point is not actually part of my graph. That's where my asymptotes intersect. So I'm going to draw a vertical dotted line as well as a horizontal dotted line. And those are my two asymptotes. That's kind of like my new x and y axis here. I'm just shifting that to wherever my asymptotes are. So normally my graph is in top right and bottom left, but because I reflected it, now my graph is top left, bottom right with that same hyperbola shape. And we're just sketching the graph. Okay, domain and range, it's always all real numbers with the exception of your asymptotes. So if I'm talking about domains, my x values, I start at negative infinity, and I'm coming, and then I jump over this asymptote and I keep going forever. So this asymptote for my x values is at x equals negative 1. So I put a negative 1 in there. Anytime you have an asymptote, we use a parentheses, and then to do my jump, I use a u. So I'm going negative infinity to negative 1, then I jump over, and I keep going from negative 1 to infinity. I just don't actually have values at negative 1. Range is the same thing, but it's always whatever your horizontal asymptote is. So I'm coming from the bottom, I'm coming up like normal, and then I jump over at 3 and keep going. So my jump is at 3, and then I go to positive infinity. All right, for this one, my A value is negative, so it reflects, and it's a 4, so it's going to stretch by 4. All right, my H value is a positive 2, my K value is a negative 1. So on my graph, I'm going to go to 2, negative 1. You can put a little dot, and I need a vertical and horizontal dotted line going through that point. So there's my my horizontal vertical asymptote. It's reflected, so I'm going to be in 2 and 4, and now I'm stretching it. So remember, to show stretching and compressing, we always did a dotted line. So if I put a dotted line for where it used to be, so that was my original graph, without being stretched and compressed, to stretch is going to pull it away from that intersection. So that means I'm going to come out here now and have that same curve, it's just it's farther away from that intersection. It's being stretched out. All right, your domain is negative infinity to whatever you're jumping over. So for the x's, I come like normal, and then I jump over 2 and keep going to positive infinity. For the range, I jump over negative 1 and keep going. So I go negative infinity, negative 1, jump, negative 1 to positive infinity. All right, for our rational equations, we're actually going to use the calculator. There's a lot written here, so you can pause and read it. But we're going to have a kind of a shortcut for how we remember this. All right, so I have, 2 functions, one on top, one on bottom. Okay, you need to make sure that you try to simplify and get rid of any common factors. All right, and your vertical asymptote is whatever the denominator equals 0. So like what we did in that first example, we're looking to see what makes it undefined. Those undefined values are where you have vertical asymptotes. Your horizontal asymptote, you have different options. Okay, so if the degree is greater on top, then there's no horizontal asymptote. If it's greater on the bottom, it's at y equals 0. And then if the degrees are the same, it's at whatever the top divided by the bottom is. Okay, now that's a lot to remember, and we have an easy way of remembering that, and that's Bobo, Bot, and Spud. All right, you just got to remember Bobo, Bot, and Spud. So Bobo is saying bigger on bottom, it's 0. All right. Bigger on bottom. That means your asymptote is at 0, so at y equals 0. Okay, bottom is saying bigger on top. You don't have one. And then spud is saying same power, you divide. You divide. Okay, and what it's talking about is like the highest exponent. So for example, if I had x cubed minus 3 over x squared plus 2x minus 3. All right, my higher degree up top is a 3, and on the bottom it's a 2. So that means it's bigger on top, so I don't have a horizontal asymptote. If it was the other way around, I had the x squared on top, it would be bigger on the bottom, and so I would have one at y equals 0. Right, and then if I said something like 4x cubed over 2x cubed plus 3x, all right, they're the same, so then I divide those coefficients. So for this one, I would do 4 divided by 2, and my horizontal asymptote would be at y equals 2. Okay, so Bobo, Bot, and Spud. All right, so we have a lot of different things that we look at whenever we look at these graphs, okay, and then we're going to actually use the calculator to help us do the actual graphing. All right, so to start with, I'm going to start by looking at my asymptotes, okay? I can't simplify anything. X plus 1 can't be simplified. X cubed can't be factored or anything. So this is the graph I'm working with. So if I look at Bobo, Bot, and Spud, all right, I have a cube on top and the first power on the bottom. So it's bigger on top. So that means that I have no horizontal asymptote. Okay, for your vertical asymptote, we're going to take the bottom and set it equal to 0. So I'm going to say x plus 1 equals 0. So then subtract the 1 over, so x equals negative 1. That's my vertical asymptote. Okay, you also need to be able to find x and y intercepts. To find your x-intercept, plug in 0 for y. To find your y-intercept, plug in 0 for x. So if we do the y-intercept first, that's the easier of the two. right? I get 0 cubed over 0 plus 1. That ends up being 0 over 1, which is just 0. So my y-intercept is at 0, 0. Your x-intercept, if I plug in 0 for my y, I'm going to end up with 0 equals this fraction. Well, no matter what, to get, like my x's, I got to move it from the denominator, so I multiply. Well, 0 times anything is 0. So whenever you find your x-intercept, you just set the top, the numerator, equal to 0. So I can ignore this bottom down here, and we say x cubed equals 0. Well, that means x has to be 0. So then my y-intercept is 0, 0. Or sorry, my x-intercept. So my x and y-intercept are 0, 0. Alright, so we got x-intercept, y-intercept. We got our horizontal and our vertical asymptotes. So next we're going to actually sketch our graph. So we're going to start by putting in those horizontal and vertical asymptotes. So on my graph, I don't have a horizontal, so I'm just going to go to x equals -1 and put a dotted line. That's the only asymptote that I've got. And then I'm going to go ahead and put my x and y-intercept, which are the same, so I'm just going to go ahead and put a point there because it's got to go through that point. Other than that, we're just going to use our calculator to help us with the graph. So in the calculator, I'm going to go to y equals, and I'm going to type in x cubed, so I can go x. Now you can go ℏ3 or press the math button, and that number 3 gets you a nice pretty cube. Divided by, now whatever goes on the bottom, put in parentheses. So I have x plus 1 because I want that whole thing on the bottom, not just the x. Then I'm going to go to my graph. I got this weird shape going on here, but that just means your calculator can't graph asymptote. So they can't like pick up and skip over. They have to always be connected. So I have this U-shaped thing going on up here, then my asymptote, then I have this snake-looking shape going on down here. So to graph that, I'm going to go ahead and put this U-shape up here, like that, and then have this graph going on here. So we're just sketching once we use our calculator to find it. And the other part you have to find is domain and range, and you're just going to use your asymptotes for that and look at your graph. So to start with domain, right, this is going to go left forever, this one's going to go right forever, and it's going to get infinitely close to this asymptote. So all I do is jump over the asymptote. So I'm going to go negative infinity, my asymptote's at -1, so I'm going to jump over. And then my range, this snake-looking graph goes up forever, down forever. So it overpowers that U shape, so my range is just going to be all real numbers. Again, you're going to use your asymptotes and just look at your graph to find your domain and range. Right? And another part of your graph is what we call point discontinuity. It's a tough one to say. But all we do is sometimes whenever we have these rational expressions, we can simplify by factoring. Well, that doesn't make that part of the graph go away. You still can't divide by 0, but like for this case, we have x plus 2, x plus 1, and then x plus 1 on the bottom. So these x plus 1s cancel. So my graph ends up being x plus 2, but I still have that x plus 1 in the bottom, which means x can't be -1. So we have what we call that discontinuity at -1. And the way we show that is just by an open circle. We skip over that one spot. So for this example, I've got x squared minus 16 on top. That's difference of squares. So I can say x plus 4, x minus 4, and then x plus 4 on the bottom. Well, those x plus 4's cancel. So my graph ends up being f of x equals x minus 4, which is linear. I go to -4 on my graph and go up 1, right 1, up 1, right 1. So we can cross out this answer choice down here. So that these three work. But then I do also have that point of discontinuity, because x plus 4 can't equal 0, so that means that x can't equal -4, right? So if I look at -4 on my graph, I've got to have this open circle, that point of discontinuity. So I have to skip over that. I don't actually have a value there. All right, so whenever you simplify, if something cancels on the bottom, you still use that to see what x can't be. That would make it undefined. It's just not an asymptote anymore because your graph keeps going. We just skip over that one point.